I want you to picture the timeline of our solar system. Go back 4.5 billion years.
It's chaos.
It's chaotic, it's violent, but the outer rim it's just dark and incredibly cold. And for a long time, we looked at that frozen wasteland and just assumed it was, chemically dead.
Right. The idea was if you want to cook up anything interesting, especially the ingredients for life, you needed a warm kitchen. You needed liquid water.
Exactly. That was the rule.
It was the prevailing view for decades. We actually call it the warm water dogma.
The warm water dogma.
I like that. The idea that life is warm and wet and fragile, so its building blocks have to be made in similar sort of cozy conditions.
But today we're unpacking a study from the Proceedings of the National Academy of Sciences that, well, it takes that dogma and just completely dismantles it.
It really does.
We're looking at the samples brought back from asteroid Bennu by the OSIRIS-REx mission. And this isn't just about, finding another cool space rock.
No, not at all. This is about finding a specific molecule, glycine, in a place where, according to all the old textbooks, it shouldn't be there.
It's a discovery that makes you ask, is the universe trying harder to create life than we ever gave it credit for? So the mission for this deep dive is to understand the seeds of Bennu. We need to figure out how a frozen rock managed to bake the building blocks of life without an oven.
And it is a fascinating detective story. It links the tiniest atomic scales, we're talking the weight of individual neutrons, to the sheer vastness of the early solar system.
So let's set the scene. The OSIRIS-REx mission. This was a massive undertaking.
Oh, huge.
We spent years flying out to this carbon-rich asteroid, Bennu, tagged it, and brought a little cupful of its dust back to Earth. Now, the expectation was we'd find carbon, right? Maybe some water locked in clays.
Right. Standard stuff for an asteroid like Bennu. And we did find those things. But the headline grabber, the thing that really caused a stir in the astrochemistry world, was finding amino acids, specifically glycine.
Okay, so for anyone who hasn't opened a biology textbook in, say, 20 years, we should probably clarify why finding an amino acid is such a big deal. We hear building blocks of life all the time in pop science. What does that actually mean here?
Think of biology like a really complex Lego castle. The proteins that make up, your muscles, your enzymes, your antibodies, that's the finished castle.
Okay.
Amino acids are the individual bricks. You simply cannot build the castle without the bricks. And glycine is the simplest, most fundamental one of all.
It's the 2x2 brick, the starter kit.
Exactly. If you find glycine, you know the chemistry is active. You know the potential for complexity is there. It's the first step on the ladder towards actual biology.
This is where the conflict comes in for me. I follow this stuff pretty closely, and I know we've found amino acids on meteorites before. The Murchison meteorite from 1969 was loaded with them.
It was, yes.
So why is finding glycine on Bennu such a paradigm shift? Why is this new paper making such waves?
It all comes down to the recipe. See, for decades, if you asked a chemist how you make glycine in space, they'd point you to one specific chemical pathway. It's called Strecker synthesis.
Strecker synthesis. This is the warm water dogma you mentioned.
Well, correct. The Strecker synthesis is a classic organic reaction. And without getting too bogged down in the formula, it essentially involves taking a few simple molecules and letting them react. But, and this is the crucial boot, for that reaction to work efficiently, you need a solvent.
You need a medium for them to move around in.
You need something for them to swim around in, bump into each other, and bond.
You need water.
You need a warm little pond, to quote Darwin. You need an environment where a parent body, a big asteroid or a planetesimal, was warm enough for long enough to have liquid water trapped inside it.
Okay, so that's the established model. You see glycine, you assume there was a warm pond somewhere in its history. But Bennu is not a warm pond.
It is far from it. Bennu is what we call a rubble pile. And the analysis of its clays and minerals, it tells a very specific story about its history. It formed way out in the outer solar system. It is, and pretty much always has been, in a deep freeze.
And the study highlights that, right? The chemical evidence says these samples have an incredibly low alteration history.
Which is just the scientific way of saying they haven't been soaked in warm water for millions of years. The mineralogy is pristine. It hasn't been cooked by hydrothermal vents or anything like that.
So you have a paradox.
You do. You have the product, the glycine, but you are missing the required environment, the warm water, to make it using the only recipe we thought we had.
It's like walking into a kitchen, finding a perfectly baked loaf of bread on the counter, but the oven is stone cold and broken.
That's a great analogy. So the scientists were left with two options. Option A, the water was there, and we just missed the evidence, which seemed really unlikely. Or option B, there's another way to bake the bread, a way that works in the freezer.
And this gets us to the core proposal of this new study. They are suggesting a completely different way to make it, one that doesn't need liquid water, but instead uses something the early solar system had just tons of.
Ice and radiation.
Ice and radiation.
Right. The technical term is solid phase radiation chemistry. It's a bit of a mouthful, but the concept is actually pretty intuitive.
Okay, break it down for us. We're talking about the time before the planets, right? The big cloud of gas and dust.
Exactly. The protoplanetary disk. Picture these little dust grains floating in the void. It's incredibly cold, so simple ices, frozen water, frozen ammonia, carbon monoxide. They just stick to these dust grains.
Like frost on a window.
A very, very cold window. Now, space isn't empty. It's filled with high-energy particles, cosmic rays, ultraviolet photons from the young sun. That's the radiation part.
So instead of a nice warm bath mixing the chemicals together, you're just zapping these frozen ice cubes with high-energy hammers.
That is the mechanism. When a high-energy cosmic ray smacks into that ice layer, it doesn't just heat it up. It breaks chemical bonds.
Yeah.
It literally shatters the molecules into what we call radicals.
And those are super reactive, right?
Highly reactive. They're atomic fragments that are desperate to bond with something, anything.
Yep.
And because they're all trapped together in that ice matrix.
They're sitting right next to other fragments.
Precisely. You shatter a carbon monoxide molecule next to a broken ammonia molecule and snap. Those fragments can link up to form something new and more complex. You do this over and over for millions of years, and you can build up structures like glycine.
So the oven in this case is actually cosmic radiation. It's providing the energy.
Yes, you don't need heat. You just need ionization energy.
Right. That fundamentally changes the map, doesn't it? Because if you need warm water, the ingredients for life are restricted to these little Goldilocks zones or the insides of big asteroids.
But if you just need ice and radiation,
Then the factory floor is the entire outer solar system.
every comet, every icy moon, every object out past Neptune could be synthesizing amino acids right now.
Okay, I have to play devil's advocate for a second. This is a great theory. Radiation did it, but how do you prove it? We have the glycine, but glycine is just a molecule C2H5NO2. How can you look at a molecule and know how it was made billions of years ago in deep space?
That is the trillion-dollar question, and this is where the study gets technically brilliant. To the naked eye, sure, glycine is glycine, but to a mass spectrometer, not all glycine is created equal. We have to talk about isotopes.
Okay, isotopes. High school chemistry flashback. These are atoms of the same element, but they have different weights.
Correct. Take carbon. Most carbon is carbon-12, 6 protons, 6 neutrons. But there's a stable, slightly heavier version called carbon-13, which has an extra neutron.
Got it.
Same thing for hydrogen and its heavy cousin, deuterium. And these heavy versions, these isotopes, they act like a chemical
A
fingerprint.
fingerprint, or more like a...
More like a thermometer, actually, a paleothermometer. This is the key insight. Chemical reactions have preferences, and those preferences change with temperature.
Wait, why? Why does the temperature change which atoms get picked for the team?
It has to do with bond strength. Heavier isotopes form slightly stronger, more stable bonds. Now, at high temperatures, like in your warm water pond, everything is moving so fast, there's so much energy, that this little preference gets washed out. Everything mixes freely. You end up with a very specific sort of average ratio of heavy to light atoms.
Okay, so warm water leaves a warm, well-mixed signature.
Exactly. But in the cold, in that freezing vacuum, the chemistry is much more sluggish. It becomes very, very selective. The reaction preferentially grabs onto those heavy isotopes because those stronger bonds are more energetically favorable in that cold state.
So if you find glycine that is unusually rich in heavy isotopes, like carbon-13 or deuterium,
It tells you it was born in the cold. It screens interstellar ice chemistry, not liquid water chemistry.
and that's what they found on Bennu.
That is the smoking gun. They compared the isotopic signature of the Bennu glycine to the glycine from the Murchison meteorite. The one we know came from a water-rich parent body.
And the difference was?
Night and day. The Murchison samples fit the warm water profile perfectly. The Bennu sample showed a massive enrichment in heavy isotopes. It pointed squarely, unequivocally, at the cold radiation pathway.
That is just incredible detective work. I mean, reading the atomic weight of a molecule to figure out the weather from 4.5 billion years ago.
It really is, and it validates the entire mission. You could never do this with a telescope. You have to physically hold the atoms and weigh them.
There's a quote from one of the co-authors, Alison Basinski, that I thought just summed it up perfectly. She said, "Our results turn the script on its head."
It's a great line, because we used to think there was one main road to get these ingredients. Now we see there's a whole highway system. There's the warm road and the cold road. And the cold road is probably much, much wider.
Okay, so we've been focused on glycine because it's the headline, the simple Lego brick. But the paper lists a whole pantry of other stuff they found. It wasn't just the one amino acid.
No, and that's so important. If it was just glycine, you could maybe argue it was a fluke or even contamination. But they found a whole suite of organic compounds. Other amino acids, yes, but also phosphates. They found nucleobases.
Okay, wait. Break those down. Phosphates and nucleobases. We're moving from proteins into genetics now, aren't we?
We absolutely are. Nucleobases are the letters of the genetic alphabet, the A, C, T, and G in your DNA.
Wow.
And phosphates. They form the backbone. They're what holds the whole genetic chain together. You cannot have a double helix without a phosphate backbone.
And they found sugars too, right? Like ribose.
Precursors to ribose, yes.
Wow.
And ribose is the R in RNA. So if you just take an inventory of what's on Bennu, you've got the components for proteins, you have the components for a genetic code, you've got the structural backbone, and you have the energy source in sugars.
It's not just a Lego brick anymore.
It's the whole kit.
It's a prebiotic starter pack.
All frozen into a rock that's just been drifting through space for eons.
This has to connect to the RNA world hypothesis, the idea that before cells, there were just these simple RNA molecules replicating. Bennu is basically saying the parts for that world are just available, off the shelf.
It strongly supports the idea that the hard part of starting life isn't making the materials. The universe seems to do that almost automatically. The hard part is just getting them all in the same place at the same time.
Which brings us to delivery. We have these seeds formed in the cold, but they don't do much good floating out past Neptune. They need to get to a planet.
And that is the role of asteroids like Bennu. We used to think of impacts as purely destructive events, and sure, the big ones are dinosaur killers. But the smaller ones,
They're delivery trucks.
they're cosmic delivery trucks. The source material uses that seeds metaphor, and I love it. Bennu isn't just a rock, it's a seed pod.
So you think about the early Earth. During the late heavy bombardment, it was just getting hammered constantly.
Constantly. And if a good percentage of those impactors were like Bennu loaded with these cold forged amino acids and sugars, they were just dusting the surface of the early Earth with organic material.
Seeding the oceans.
Literally. They land, the ice melts, and the seeds dissolve into the water. Now you have your warm pond, but the ingredients didn't have to be made in the pond. They were imported from the freezer aisle of the solar system.
It totally reframes how you look at the night sky. It's not a void, it's a distribution network.
And it suggests this process is universal. If this chemistry works on Bennu, it works in other solar systems. It relies on physics that is the same everywhere.
That's the staggering part. If the warm water dogma was the only way, life might be incredibly rare, because warm ponds in space are rare. But if this cold radiation pathway is true,
Then the ingredients for life are chemically inevitable. They're a natural byproduct of star formation. You have a star, you have dust, you have ice, you have radiation, you get amino acids, period.
it's a humbling thought. We look at Bennu, this dark, charcoal-black rubble pile, and we see a curiosity. But in reality, rocks like that might actually be our ancestors.
Or at least the vehicles that brought our chemical ancestors to the party. We are, in a very real sense, connected to that cold, dark chemistry. The line between Earth biology and space chemistry is totally artificial. It's all one continuous process.
So to recap the mission of today's deep dive, we looked at the samples from Bennu, we found the building blocks of life, we learned the old warm water rules don't always apply, and that cosmic radiation can forge these molecules in the deepest freeze of space.
And we confirmed it with isotopic fingerprints. We know this coal pathway is real, it's robust, and it's likely happening all across the universe. It turns the emergence of life from, say, a lucky lottery ticket into something that looks a lot more like a cosmic default.
A cosmic default. I like that. And that is the thought I want to leave you with. If the universe is a factory that automatically produces the seeds of life in every dark, cold corner and then scatters them across solar systems, are we really that special? Or are we just what happens when one of those seeds finally finds some good soil?
It's the ultimate question, isn't it? It certainly makes the galaxy feel a little less empty.
Thanks for exploring the origins of well, of us, with us today. Keep looking up.
And stay curious.